Hello everyone. This video is on the Knewton Alta assignment for section 5.5 part 2 called Complex Zeros of Polynomial Functions. Alright, so in this video I'm going to be doing a preview version of this assignment, so please understand that the questions I see in this video may or may not be the same questions that you see when you work on the assignment yourself. But the objectives are the same, so I'm hoping that watching me do a few examples here helps you in some way when you work on it on your own. Alright, so on your assignment page you should see the title, your mastery bar, the objectives. Oh, it looks like there's only the one objective here. And then underneath the objective, the current objective, there should be a question related to it. And then at the bottom of every question you should see a feedback button where you can send feedback to Knewton. You will not have this instructor cheat button. That's for instructors only. But you will have this more instruction button. Right? So if you're struggling with a topic, try clicking on this and you'll be taken to a page with some reading or some videos to watch, and then you'll be given questions related to that instruction, and you can get through the assignment that way if you wish. Alright, so the only objective here is find zeros of polynomial functions with complex zeros. Now remember, complex numbers, every number is complex. The real numbers, the imaginary numbers, any combination of those two, real plus imaginary, everything's complex. So basically what we're asked to find here is, we're given a polynomial and we're asked to just find, what numbers, real, imaginary, combination of the two, what complex numbers can I plug in for x, or whatever the variable is, and get an output of 0. And we're going to make heavy use of the rational zero theorem here. So I hope you recall section 5.5 part 1 on the rational zero theorem, because I'm not going to state the theorem again, I'm just going to be using it. And yeah, so let's go. So the first question, polynomial f of x given below has 1 as a 0. So this one's even easier. They're telling you one of the zeros. They're asking you to define the other two, right? It's a degree 3 polynomial. Whatever the degree is, that's how many complex zeros the polynomial will have. All right? So a degree 3 polynomial will have 3 complex zeros. So they gave us one of them, the number 1. What are the other two? Alright, so then we're going to go back to, again, section 5.5 part 1 talked about the factor theorem. If 1 is a 0, then x minus 1 is a factor. And I can use that in some division to find another factor. We can try to factor this polynomial completely and find all the zeros of all the factors. Alright, so write this out. Alright, the polynomial we're given here is f of x equals, we have x cubed plus 3x squared plus 16x minus 20. Alright, and they're telling us, they told us that x equals 1 is a 0. Meaning that when and you can easily see that 1 plus 3 plus 16 is 20, minus 20 would be 0. Right. And as I was saying from the factor theorem, right, that means that the quantity x minus 1 is a factor, and once you know a factor, you can find another factor by dividing. Now, you can do law division. Take this polynomial, this degree 3 polynomial, and divide by x minus 1. And then the remainder should be 0, right, if it's a factor, and then the quotient will be your other factor. Or you can do synthetic division, right? This is a degree 1 with a lead coefficient of 1. So I can do synthetic division, and I'm going to do it the same way I've been doing all these other videos. 1 is a 0. Right, so I put 1 here in the lower left corner. Up top, the coefficients of the polynomial we're plugging into, 1x cubed, 3x squared, 16x to the first, and then negative 20 for the constant term, then a bar here, separating the quotient from remainder. And again, I hope that the remainder is 0. The remainder had better be 0 if x minus 1 truly is a factor. And then I perform the synthetic division. Drop the first coefficient. 1 times 1 is 1, plus 3 is 4. 1 times 4 is 4, plus 16 is 20. 1 times 20 is 20, plus negative 20 is 0. Hooray, right? So what they said was correct. But now that I know I have a 0 and a factor, I can find, I can factor the polynomial now. Right? So instead of f of x equals, this whole degree 3, if I've got 1 here, that means, we're dividing by x minus 1 times, and then here, the 1, 4, 20, these numbers are the coefficients of the quotient in descending order. And it would be a degree 2 polynomial, right? Because again, the last one's a constant term, constant first power, second power. So 1x squared plus 4x plus 20. All right, so I can factor it, and we know what makes this factor 0. That's x equals 1. Now we just look at the other one, the other quadratic one. This is not factorable. There are not factors of 20 that add up to 4. But we're going to find the zeros of this polynomial now. Now it is a quadratic. Right, we're basically, again, just setting it, what makes it 0, solving this equation. You can use the quadratic formula. I'm going to do completing the square this time. I've done the quadratic formula a bunch recently. So remember, you complete the square on x squared plus 4x, you would have to add 4. Do that to the other side as well. This is x plus 2 squared equals negative 16. Square root property, x plus 2 equals positive or negative 4i. Right? Remember, the square root of negative 16 would be 4 times I, right? 4 times the square root of negative 1. And then subtracting 2, here we go. Negative 2 plus or minus 4i. And there they go. And there's the other two zeros. So negative 2 plus 4i, negative 2 minus 4i. Those numbers are also zeros of this polynomial. So 1 works, but so do these. And you can check them. Plug in negative 2 plus 4i for x and then multiply it out. Now that would be kind of annoying. And remember also that, I squared is negative 1, I cubed is negative I, and all that. And you would simplify, and it would end up simplifying to be 0. Right? But I know I did this correctly, so I'm just going to take my own word for it here. So the other zeros that they're asking for are, negative 2 plus 4i and negative 2 minus 4i. Oops, I capitalized I. All right. That's it. That's all they want. And then after you submit an answer, it should give you some sort of answer explanation afterwards. Please read through these. Alright, so you can hopefully understand why something was correct or incorrect, especially incorrect, and you can try to learn from your mistakes for future questions. Alright, next. Alright, so once again, we're given a 0. Now, normally, if you're given a polynomial with integer coefficients, notice all the coefficients are integers, 1, 9, 43, and 75, you can apply the rational 0 theorem. Right? Make a list of possible rational zeros, and then you start checking the numbers on that list until you find a 0, and then you go factor. But they've been very kind to us so far, and just giving us one of the zeros, and we have to find the other ones. Alright, so again, it's a degree 3 polynomial, so there should be 3 complex zeros. They give us one of them, negative 3. If you plug in negative 3 for x, the output will be 0. We want to find the other 2, right, and put them in these boxes down here. Okay, so very similar setup to this last example. So we have x cubed plus 9x squared plus 43x plus 75. And again, we're told that negative 3 is a 0. x equals negative 3 is a 0. Find the other ones. Right, so I'm doing division. All right, again, synthetic division, make it easy. So negative 3 here, the coefficients of the polynomial up top, 1x cubed, 9x squared, 43x to the first, 75 is the constant term. And again, I want, if what they said is correct, there should be a remainder of 0. So drop the 1. 1 times negative 3 is negative 3 plus 9 is 6. Times negative 3 is negative 18. Plus 43 is 25. And then negative 3 times 25, negative 75 plus 0. Hooray. All right, so that's correct. Negative 3 is a 0. And now I can use this line to factor the polynomial, right? F of x, instead of being this degree 3, is x plus 3, right? If negative 3 is a 0, then x plus 3 was a factor. And then these numbers here, the coefficients of the quotient, right? The other factor, would be x squared plus 6x plus 25. Right, and now I want to find the zeros of this polynomial. And this is not factorable, so let's do this. 1 is x squared plus 6x plus 25. When is that equal to 0? And again, it's a quadratic. You can use the quadratic formula. I'm once again going to complete the square. So we have x squared plus 6x equals negative 25, and then I would have to add 9 to both sides to complete the square. Then this left side is the quantity x plus 3 squared. This side is negative 16. Square root property, x plus 3 would be positive or negative. The square root of negative 16 is again 4 times I. Right, the square root of 16 times I. And then subtracting 3, we get our other two zeros. Negative 3 plus 4i, negative 3 minus 4i. All right, but they do have an imaginary number in them. Right? But it doesn't matter. Right? We're asked to find the complex zeros. Every number is complex, with an imaginary or not. All right, so negative 3 plus 4i is one of them. Negative 3 minus 4i is the other. Great. Okay. Next, again, the same objective. I hope they make it a little more difficult. Aha. So here we're asked to find the real and complex zeros. So basically just find all the zeros of this polynomial. And again, it's a degree 3. Degree 3. So we should be finding 3 complex zeros. And it says express your answer as a list separated by commas. No plus or minus signs, right? Separate them. And don't put the x equals, right? Just write the numbers separated by commas. All right, so I'll write this out. Now here, this is one where we're not told a 0. Right? They didn't tell us any of the zeros. But we can help. We can do something still. Just because we don't know any of the zeros doesn't mean we're helpless. So we have 3x cubed minus 4x squared plus 11x plus 10. All right, so again, notice all the coefficients of this polynomial are integers. 3, negative 4, positive 11, positive 10. All the coefficients are integers. So we can apply the rational zero theorem, which again was from section 5.5 part 1, if you look back at that. So by the rational zero theorem, if this function, right, if this polynomial f has any rational number zeros, or just rational zeros, they will look like the following, or they will take the following form. They will look like, x equals, and again, hopefully this rings a bell, but the numerator of any rational zero this might have has got to be a factor of the constant term, some factor of 10. And the denominator must be some factor of the lead coefficient, right? So some factor of 3. and we're going to use this information to make a list of possible rational zeros for this function and start checking the numbers on that list. So factors of 10 are 1, plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. And then the factors of 3 are 1 and 3. Again, don't need the minuses down here because I got them in the numerator. And then from this, we can make a list then, a list of possible. And I do emphasize the word possible. Just because I'm making this list doesn't mean that one of these numbers is going to work. A list of possible rational zeros for f would be every combination of these. So 1 over 1, so positive or negative 1. 1 over 3, positive or negative 1/3. 2 over 1, positive or negative 2. 2/3, right, positive or negative 2/3. And 5 over 1, positive or negative 5. 5 over 3, right, positive or negative 5/3. 10 over 1, and 10 over 3, right? So positive or negative 10/3 as well. So that's a big list. That's a pretty big list. There are 16 different numbers on this list that we're going to check. All right. Now a couple of them I can do mentally, like 1 and negative 1. Right? So again, we check for zeros on this list, and once we find a 0, then we can do it like the previous two examples. Once you know a 0, you can factor the polynomial, and once you factor a polynomial to degree 1 and degree 2 factors, you should be able to state all the zeros pretty easily using the quadratic formula or something. All right, now f of 1 would be, 3 minus 4 is negative 1. Plus 21 would be 20. So no. F of negative, I'm not doing synthetic division for these 1 and negative 1 because those are usually pretty easy to check on your own. Now if I plug in negative 1, you'd have negative 3 minus 4 is negative 7, right? And then negative 7 minus 11 be negative 18 plus 10 is negative 8. So no again. All right, but here's something you should know too. See how when I plugged in negative 1, got negative 8, a negative number. When I plugged in positive 1, I got positive 20, right, a positive number. So based on these two, there's that thing called the intermediate value theorem that you may have read about in section 5.5. By the intermediate value theorem, this function has, because it's continuous, has to have a 0 between negative 1 and positive 1. So f has a 0 between at least 1 0 between x equals negative 1 and x equals positive 1. So this leads me to checking the fractions, 1/3, 2/3 here. All right, those are 1/3, negative 1/3, 2/3, negative 2/3. Those are between negative 1 and 1. Now they might not work. Right? The zeros between negative 1 and 1 might not be rational. They could be irrational. Right? But there's got to be one. There's got to be at least one. All right, so now I'm going to go into synthetic division. And we'll start checking these. So I make my synthetic division symbol thing here. I'm going to plug in, I'll try 1/3 first. And then the polynomial coefficients up top, right? The polynomial that we're plugging into, 3x cubed, negative 4x squared, positive 11x, positive 10. All right, drop the first thing. 1/3 of 3 is 1, minus 4 is negative 3. 1/3 of negative 3 is negative 1, plus 11 is 10, and then, that's not nice. All right, yeah, it's 1, minus 4 is negative 3, and then, yeah, negative 1 plus 11 is 10, and then 10/3 plus 30/3 would be, 40/3 for the output there. Okay, so positive 1/3 doesn't work. How about negative 1/3? So again, drop the 3. And that's negative 1. This won't work either. Negative 1 minus 4 is negative 5. And then you got positive 5 thirds, plus 33 thirds is 28 thirds. And we have negative 28 ninths plus 90 ninths would be 62 ninths. It's like, no. How about negative 2 thirds? The only reason I'm saying that is because I have a positive output at negative 1/3 and a negative output at negative 1. So some number between negative 1 and negative 1/3, got to make this 0. So may as well be negative 2/3. Let's check that out. So, and then, again, negative 2/3 is on the list. It's got to be on the list. Don't check anything else. All right, just check numbers from the list of possible rational zeros. All right, so drop the 3. Then this is negative 2 minus 4 is negative 6. Then positive 4 plus 11 is 15. Hey. Negative 10 plus 10 is 0. Fantastic. So negative 2/3 is a rational 0 of this polynomial. And so now we can factor it. Now I have a 0. F of negative 2/3 equals 0. We can factor this thing. So f of x equals, now remember, if negative 2/3 was here, that means I was dividing by x plus 2/3. A degree 1 with a linear coefficient of 1. That's the only way you can use synthetic division. And then these numbers here are for the quotient 3x squared minus 6x, then plus 15. And you're going to notice this with fraction zeros when you do synthetic division. If a fraction is a 0 for a polynomial with integer coefficients, you're going to notice that the quotient all have a common factor. Like all these have a common factor of 3. So I'm going to pull that out. And that's the lead coefficient of the polynomial too, this factor of 3 that they all have in common. So I pull out the factor of 3 from these, and then we have times, x plus 2/3. And then when I pull a factor of 3 out of this quadratic here, we'd have x squared minus 2x, and then plus 5 left over. Okay, and then we just need to look at this quadratic now. When is that 0? All right, so when is x squared minus 2x plus 5 equal to 0? And again, you can use the quadratic formula or complete the square, which I'll do again. So subtract 5, then add 1 to both sides. We got x minus 1 squared over here equals negative 4, and then square root property. All right, the square root of negative 4 is 2i. All right, then, so we have x minus 1 must be plus or minus 2i, and then adding 1 to both sides. 1 plus or minus 2i. So there's the zeros, there's a 0. All right, there's your 3 zeros. Negative 2/3, 1 plus 2i, 1 minus 2i. And that's what I'll type in. And you can check by plugging those in. It would be a while, but those actually make the output 0. They should. So negative 2/3, comma, 1 plus 2i, comma, 1 minus 2i. Right, those are your 3 zeros separated by commas. Great. Again, see, they're doing the synthetic division, first making that list of possible rational zeros and check. They find negative 2/3 works, right? And then, then they factor the thing, take the quadratic factor, find, they use the quadratic formula. Same thing, right? Same stuff. Pardon me. All right, there should just be one more of these. Okay, same deal. All right, another third degree. Again, I think they're just giving you third degree polynomials, so you only have to do this once, do the process once. The higher the degree, it just gets more tedious. If it's a degree 4 polynomial, once you find a 0, you'll break it up to a degree 1 times a degree 3. And then you just kind of start over with that degree 3 factor. And then, so the process just repeats. So I think that's why they're giving us just degree 3 problems here. So we don't have to keep repeating the same thing over and over again. But again, we're asked to just find all the zeros, right? Real and complex, just all the complex zeros of this polynomial. And wow, I don't even need to use the rational zero theorem here. This is factorable by grouping. So let me show you. Not all of them are, like this polynomial we got in this last example. This is not factorable by grouping, but they're being again very very kind to us. F of x equals x cubed minus 14x squared plus 3x minus 42. If you look at the first two terms, pull out x squared. It'd be x squared times x minus 14. Plus, and then look at the next two terms. They have a common factor of 3. If you pull out a 3, you'd have 3 times x minus 14. All right, 3 times 14 is 42 as well. And then you look at the whole thing. Both these products here have x minus 14 in common. And there we go. It is factored. X minus 14 times x squared plus 3. So one of the zeros is clearly 14. Right? Because x minus 14 is a factor. And then when is x squared plus 3 equal to 0? Well, that's when x equals positive or negative square root of 3 times I, right? Because you have or I times the square root of 3, but you'd have the square root of negative 3 or negative square root of negative 3. And there we go. I'm done. All right, that was a quick one. Now, if you didn't see this, if you didn't see the grouping, you could make that list of possible rational zeros. Which would just be the factors of negative 42, because the denominator would be just 1. Right? These are all integer coefficients that can apply the rational zero theorem. Any rational zero, the numerator's got to be a factor of 42, the denominator's got to be 1. Right? So the factors of 42, plus or minus 1, plus or minus 42. Plus or minus 2, plus or minus 21, plus or minus 3, plus or minus 14. No 4, no 5, 6, right? Plus or minus 6, plus or minus 7, and that's it. Right? There's your list of possible rational zeros. And if you start checking all these, the only one that works is 14. All right, let me go make synthetic division here. Say you were checking a bunch. You get down to 14, it's going to work, right? You got 1x cubed, negative 14x squared, positive 3x, negative 42. Drop the 1, then 14 minus 14 is 0, 0 plus 3 is 3, and then 42 minus 42 is 0, so you get a 0 there. And you factor to x minus 14 times x squared plus 0x plus 3. And it's exactly the same stuff that I got earlier, factoring by grouping. Alright, it just would have taken longer because you had to check this list of possible rational zeros. Alright, but the zeros are 14, square root of 3 times I, negative square root of 3 times I. And that's what I'll enter, and again separated by commas. 14, comma, square root of 3, and then get out of the square root, right? Make sure the I is not inside the square root. In fact, most people will probably write I times the square root of 3, just to make sure. And then negative square root of 3. Get out of the square root, and then times I. That should be good. Wonderful. And again, you can check all those, plug them in for x, make sure you get an output of 0, and you should. See, they did the thing with the list. Again, if you see a way to do it faster like I did, or if you see, oh, this is factorable by grouping, just do that. Nothing wrong with that. However you can find the zeros, find them. Alright, and that should be it for this preview version of this assignment. Right, as I said at the top of the video, the questions I saw here may not be the same questions that you see when you work on the assignment yourself, but the objectives are the same. So I'm hoping that watching me do these examples here help you in some way when you work on the assignment on your own. And thank you very much for watching.